Okay, so let's go to question number 7. In which direction will the net reaction proceed for each of these sets of initial conditions? So we have a condition where all of the concentrations are the same. And then for B, we have the same pressure for X and Z, but a different pressure for Y. Okay, so I'm going to write down the net reaction. X plus Y is in equilibrium with Z. Then Kp equal to 1 atmosphere. Oh, it's just 1, sorry. At 300 Kelvin. So the first thing I'm going to do is calculate delta N. And to do that, it's going to be the number of moles of your products minus number of moles of your reactants. And then it's going to be 1 minus 1 plus 1. So delta N is equal to -1. Okay, so for part A, first we need to calculate the value for Kc. So this is the equilibrium constant for the concentrations. So then to solve for Kc, I'm going to use the following equation. For Kp, so the equilibrium constant for the pressure, is equal to Kc times RT to the power of delta N. So I know that Kp is equal to 1. Kc is what we are trying to solve for. And then in the brackets, I'm going to use the R constant, 0.0821 liters times atmosphere over mole times Kelvin. So there's a lot of different R constants out there, so make sure you use the right one. So for instance, I'm using this value for R because of the units it's in. So for T, I put in my 300K. And then all of this to the power of -1. Okay, so now let's solve for Kc. If we try to simplify this expression, then we get the following. Okay, so you'll see our ATM cancels out. And the Kelvins cancel out as well. Then our Kc value is then equal to 24.63 at equilibrium. So now that we have Kc, the second part of part A is that we need to calculate the value of Q. So basically the reaction that is not present in equilibrium is equal to Q. And basically Q is equal to the concentration of your product over the concentration of your reactants. So I'm just going to plug in the concentration values so they all equal 1. So this gives us a Q value of 1 for QC. So since QC is less than Kc, then that means the reaction will go to the right. Okay, so that was for part A. Now let's look at part B. So this is 7B. We're going to do something similar, except this time let's calculate for QP since KP is given. So QP is the pressure of your products over the pressure of your reactants. So it's going to be 1 over 1 times 0.5 and then you should get a QP value of 2. So if we know that Kp is equal to 1, then that means QP is greater than Kp. So therefore this reaction will go to the left. Okay, so let's see what our junior tutor said. Woo. Okay. First, let's define equilibrium constant for any species. So that relates product and reactants distribution. It is similar to a ratio. So first they calculated A at equilibrium. They found the Q for concentrations. And then they calculated for Kc. Let me go back to my page. 24.6. Yep. And then they wrote down all the different types of scenarios that you could get. Since 1 is less than 24.6, Q is less than K, Therefore, expect reactants to form more products in order to achieve equilibrium. So reaction will go to the right, basically. And then for part B, they calculated PKP, or QP, I mean, and got 2. So QP is greater than KP. This has much more products than reactants. Therefore, expect products to form more reactants in order to achieve equilibrium. So the reaction will go to the left. So this solution is correct.